On the slide here, I will talk about homogenization in context of extended continuum series. Today I would like to restrict on the second gradient and the micromorphic one, and at the end I also would like to show an example which is related to such a single pore or hollow sphere model. Well, even more professional now. It's a work where a lot of discussions are included and some hints. Also, in particular, I would like to acknowledge the contributions of Samuel Forrest and Karam Saab, which have taken place since the last meeting 2 years ago. Well, the first slide I think I can leave away. The motivation is, of course, that we are interested in materials with microstructure and internal length scales. Could be such open cell structures or also metal structures with small pores, micropores. And the idea is, how can we model such materials in an effective manner on a large scale where we don't see the internal length scale, but where we, of course, observe the effects of the internal length scale. That's our goal. That's why we would like to interpret material parameters in extended continuum series. The outline, very fast. As I said, I would like to consider second gradient and also micromorphic model. I will just repeat in a very short manner the basics of these two extended continuum series, how I use them. The main part will be the upscaling. So I will start for both cases with the extended form of Hill-Mandel criterion. I will introduce some strain averaging rules, and afterwards I will try to derive kinematic and that's new stress boundary conditions, or how we think they should look like. At the end, a very simple numerical example. So since my PC is not working, you do not see an animated picture here. We will try to improvise at the end. So, but first, in a nutshell, the second gradient model, which I'm quite sure most of you are quite familiar with. So the idea is, so for the resolution, is that we enrich our continuum model by the second gradient of the displacement field, so by the gradient of the strain. And of course, on the side of the external, or the power of the external forces, we could do the same, but as we have already discussed these days, sometimes a little bit hard to motivate the higher boundary conditions. We could also ignore them if we like, but at the end, in any case, we end up with such a kind of balance of momentum where we consider divergence of the stress and a higher derivative of the double stress. And of course, some boundary conditions here for the surface tractions, or if needed, also for surface couples. This concept goes back on the works of Mindlin. The principle of virtual work was described in Germain, in his famous papers from '73. And later on, we will compare to some contributions by Gologanou and Leblanc. The micromorphic model is a little bit different from the kinematical point of view. You see, for the internal power, we have three contributions. The strain, second, or here's the strain velocity, but it's not the difference here. Second, something we call microdeformation, in this case microdeformation velocity. And third, the gradient of the microdeformation. And on the side of the external forces, again, something like a surface traction, and if we like, something like a surface moment or double force. And now the balance laws look a little bit different. First, we see something like the standard balance of momentum, and we end up with a with a coupled second balance equation, the balance of momentum moment somehow. But here it's not only angular momentum, but also linear momentum, for instance. And here the boundary conditions. This concept goes back on the works of Ehring and again Germain. So our idea is now, or our problem first is now, that these extended continuum series include a various set of material parameters, which are usually not such easy to evaluate in physical experiments. And we will try, or we would like to try out to identify them by microscale computation. So assume if you have such a heterogeneous microscale with some internal length scales, what can we do? How can we interpret this heterogeneous standard Cauchy medium? How can we substitute it by a homogeneous but extended macro continuum? And how can this scale transition rules look like? So in the typical way we walk here is first we find something like energy criterion comparing the power in a macroscopic material point, comparing with the volume average with the power of such a representative volume element. We would like to define volume averaging rules for kinematic and stress quantities, and we would like to define different types of boundary conditions. First for the second gradient case, and now I use the formulation of Leblanc et Goulaganou, which, yes, since the second gradient refers to the strain gradient and the strain gradient and the strain itself, and the assumption is that we could impose polynomial loading condition of quadratic form, where the linear part refers to the strain and the quadratic part refers to the strain gradient. We just discussed about this point this morning. There also are some problems related to. Second, now the stress criterion, extended form of Hill-Mandel criterion. On the left-hand side, the volume average of the standard medium here inside. Just one contribution, sigma times velocity or strain gradient, times strain, minus the macroscopic contributions, so the stress and the dual or double stress. And if you insert in a certain manner these boundary conditions here in this equation, you have to transform into a surface integral and so on. We are in the position to derive stress homogenization rules, so we impose kinematic boundary conditions and we end up with some stress homogenization rules. Now the micromorphic case, where the problem is a little bit more difficult, since it's not really clear how could the averaging rules look like here, because there's not something like a second gradient which you also can find on a microscale, but we have something like a micro deformation not existing on a microscale. And Samuel Forrest and Karam Saab had the idea to compare the effective or the real displacement field with the micromorphic affine extension to compute the minimum, and this leads, which cannot be read here, to three different volume averaging assumptions. The first one, the macroscopic strain can be computed as the volume average of the microscopic strain, but we have to consider that principally the macroscopic strain could also be asymmetric. Second, the micro deformation, which is not such natural, it's the volume average, you cannot read it, of something like the displacement field times x, so it's the first moment of the displacement field multiplied by such an inverse g, where g is just the second moment of our volume element. And third, averaging rule for the curvature, which is basically the derivative of this part here. If we would like to introduce boundary conditions, we of course need to transform these volume averaging rules into surface averaging rules. But then we see here, if that's the first moment, it's not possible. There's no derivative inside. It always will stay such a volume integral, and by consequence, it's not straightforwardly possible to impose directly boundary conditions here. That's the consequence somehow of this strange structure of averaging rules. But of course, we can make some assumptions. We can introduce a fluctuation field and impose cubic polynomial boundary conditions on the boundary. And for some cellular structures, we have tried out and found quite good results, but only for very simple structures, something like this. But the problems remain valid. The first one, we have no general access to the boundary, so directly boundary conditions are really difficult to handle. And the second, if we would like to introduce such a cubic polynomial, or also a higher order polynomial, the choice of the polynomial coefficients is not unique. So we can have some assumptions and we can try out if it works, but it's not really satisfying because there's always a lot of assumption inside. And that's why we asked ourselves if it would be possible to impose stress boundary conditions or loading conditions instead of kinematic boundary conditions. And that's the main idea of this talk. The main idea, or the basis for that, if I go back, was that what we know the volume averaging rules. Second, we know the Hill-Mandel condition. And the idea was now just to impose here on the right-hand side where you find the macroscopic deformation quantities, the volume averaging rules, which we just identified. And if we do it in a clever manner, and if we evaluate now the Hill-Mandel condition, and furthermore, if we assume for the left-hand side where you find the small scale, the volume average of the small scale, a certain structure, which you find here, it means we can supply or we can impose stress loading conditions via the surface and by some similar to a volume force. Yeah? So the balance of momentum is not equals 0, but equals minus B, which is controlled by overall stresses. That's the basic idea. So then the volume integral of the stress power transforms into the sum of the surface actions and some volume actions, and both are controlled by macroscopic stress quantities. And if we evaluate in this way, after some calculations, we are really able to define in a unique manner stress and then now say loading conditions, because only one part takes place on the boundary. It's a linear part, so first we have a constant contribution of the overall stress, but there is also a linear contribution of the double stress, and second we have also a linear supply in the volume where enters this hyperstress S and also some contribution of the double stress, but this is mainly for balance, to satisfy the balance of force here. Yeah, and now the idea was we should make a numerical study, and we would like, this is only the first numerical study, we wanted to restrict to a problem as simple as possible, and we found this study by Goulet-Ganou and Leblanc, where they considered a hollow sphere problem based on Gerson's idea, but they applied higher order boundary conditions. In particular, they applied quadratic boundary conditions, which you cannot read anymore here. On the surface, a quadratic polynomial, as I showed before, the first, so the linear part goes with the strain, and the second, the quadratic part, goes with the strain gradient. And our idea was, okay, they have the polynomial, we have the stress loading conditions. It would be nice to make a limit analysis for this case and compare the results. Of course, you might know that limit analysis in terms of stress loading conditions is kind of, or stress control is kind of difficult, since we are interested in the plateau, in the stress-strain relation. But what we also learned from our results before, that there's an equivalence between our stress loading conditions and the volume averaging rules. So if we impose the volume averaging rules as something like a volume constraint in a weak form, or if we impose the stress loading conditions, should be equivalent at the end. And that's exactly how we managed to perform limit analysis here for this case, not applying the stress loading conditions, but the equivalent volume averaging rules. And I see I have to hurry up. So then I come, usually there should be some movies which I cannot show it to you now. In this hollow sphere problem considered by Goulet-Ganou and Leblanc is axis symmetric. You see here the two-dimensional plot. The symmetry axis is the E3 axis, and in this case only 4 independent deformation modes remain active. First, the volumetric strain and the deviatoric strain. On the left-hand side, you would see, if you could, the case of the polynomial loading. And I compared here. You see some stress-strain relations. The lines themselves refer to the polynomial loading. The dotted lines refer to the volume constraints. The first we see is that the stiffness, you can recognize here, of the dotted lines is always lower than the stiffness of the lines itself. It means that's also how we expected. Stress loading conditions should be softer or produce softer effective stiffness than kinematic loading conditions. That's what we already know before. And you also see here the plateaus for different porosities starting from 1/10 to 30%. And here you see the yield surface or the limit case of the yield surface, where the blue boxes refer to the polynomial prediction in the linear case, though there's no extension so far. And these triangles refer to stress loading conditions or the volume average constraints. And you see in this case of the linear modes, there's not such a big difference. The yield surface becomes smaller for higher porosities, but the difference between the triangles and the boxes is not such big. Now we come to the extended case. For the polynomial loading, case 1, it means two strain or two coefficients of the strain gradient remain active. The first one is something like the mean strain with respect to the first two indices, and for the same two base systems, the deviatoric strain. And again, we compare the polynomial loading and the loading by volume averaging. And first, again, some curves here for the different loadings. We see now there is a big difference in the limit and the plateau value for these two types of loading conditions. And if we go in the hyper or double stress space, we first see again the boxes referring to the polynomial loading. In particular, in the work of Gologanu and Leblanc, they have computed or have found also an analytical solution for this blue line, which we could also reproduce here. If you increase porosity, this becomes smaller again. And now the really strange thing is, which puzzles us at the moment, is that if we impose volume averaging constraints here, we are not able, with these two kinematic measures we can control, we are not able to produce a yield surface here. We just find for each porosity one single point in this stress plane here. Moreover, these points are outside of the polynomial yield surface, and for these two strange things we have also two ideas, but we are not sure if these explanations are correct. The first one, why it could be outside, could be explained that for this case we have a polynomial referring to a strain gradient continuum, but here we have evaluated volume averaging rules for a micromorphic continuum, so the definition of the stresses is not one by one the same. Could be the first explanation. Second, the question why we only find certain points here and why we cannot produce really surfaces here. Our idea is that maybe the axisymmetric case is too restricted in strains, since there are only two higher modes active, and this we will try it in future. So just in a few seconds, the basic ideas. So for micromorphic media, the definition of Dirichlet boundary conditions is not such clear, but we were able to define Neumann boundary conditions where we have to work in future. Thanks for your attention.
Thank you very much. Some questions? In your limit case that you have shown the 2 points that you have, what is the distribution of plastic deformation or stresses in your unit cell?
So in the unit cell, I mean, the problem is, of course, if we have this volume averaging rules here, is that we have to consider the cavity. We can introduce a cavity strain model, or we fill the cavity with a very soft medium. In this case, I have chosen this way to evaluate the volume averages, and at the end, this very soft medium is, of course, able to capture most of the deformation. So in these computations here, almost 70% of the deformation took place inside of the cavity, so there does not remain so much for the matrix material. But at the end, the interesting thing is all the deformation modes we impose here end up in the same flow picture at the end.
Okay, then thank you, Dave.